Welcome to the class of stochastic processes. We first introduce a few definitions. Number one, rho ij. Rho ij represents the conditional probability that the process starts from state I and the first heating time of state j is less than infinity. So that is the conditional probability that given x0 is I and the heating j in finite time. So we have one remark here. If I is recurrent, that means the process starts from I. Eventually, the process will hit I again. So rho I must be 1. On the other hand, if I is transient, that means there is positive probability that the process starts from I but will not return to I. So rho I must be less than 1. But of course, rho I will be greater than or equal to 0 because rho I represents conditional probability. Second, Nj represents total number of visiting j in finite time. So we can let Nj be summation delta j xn. And the function delta j k is equal to 1 if k is equal to j, and 0 if k is not equal to j. So every time we check if the process, the state of the process represented by k, if this is equal to j, if it is equal to j, this is 1. Otherwise, this is 0. We use the following process as an example. So this is the process, and this is the j we are interested in here. So every time the process hits j, delta jk will be 1. So we have 1, and then 1, 1, 1, 1. So totally we have 5 ones. So nj will be summation of 1 5 times. So nj will be 5. So that means the process hit j 5 times. Some properties for nj. First, pi nj greater than or equal to 1. That means the process starts from state I and at least hit state j for 1 time. So tj less than infinity. So that is rho ij. Pi nj greater than or equal to 2. That means the process starts from I and the process will reach state j at m step, and then from j, the process will reach j again at n step. So, and we take summation over all possible m and n. So we look at the inside here. So summation pi tj is equal to m and take summation over all possible m. That is exactly pi tj less than infinity. And because this has nothing to do with n, so we can move it outside of the summation. That is rho ij. And inside of the summation, summation n and pj tj is equal to n. This is exactly pj tj less than infinity. So overall, we have rho ij and rho jj. And similarly, pi nj greater than or equal to 3, that is rho ij. So we hit j for the first time. And then from j, we hit j the second time, rho jj. And the third time, rho jj again. So overall, we have rho ij, rho jj squared. And similarly, pi nj greater than or equal to m. This is rho ij and rho jj to the power of m minus 1. So totally, the process will hit j m times because we have hit j 1 time here and m minus 1 time here, right? So totally, we hit j m times. And if we would like to compute the conditional probability pi nj is equal to m, we could use pi nj is greater than or equal to m minus pi nj is greater than or equal to m plus 1. So that is rho ij, rho jj to the power of m minus 1 minus rho jj, rho ij, rho jj to the power of n. So we have the final result here. And the Pinj is equal to 0. This simply means the process will never hit the state j. So that is 1 minus rho ij. 1D in homogeneous random walk. Previously, we talked about random walk, by which we mean homogeneous random walk. Homogeneous random walk means the process has the same probability of going right or going left, regardless of where the process is. However, when it comes to inhomogeneous random walk, it means the probability can be different dependent upon where the process is. In particular, here we are interested in this quantity. Conditional probability of the process start from 1. What is the probability that the process will reach 0 before it reaches D? So pictorially, we can show it like this. So the process starts from 1. And what is the probability that the process will reach 0 before it reaches D? And because this is inhomogeneous random walk, so Pij, that means the process starts from state I and will go to J. When J is equal to I plus 1, that means the process will go right, and the probability is Pi. If J is equal to I, that means the process will remain in the same place, so the probability is Ri. If J is equal to I minus 1, that means the process will go left. The probability is equal to Qi. So we generalize this quantity. We let x0 in general be I, and we were interested in Ui, which is the conditional probability that the process will reach 0 before it reaches D. So obviously U0 is equal to 1 because U0 means the process starts with 0 and then the process will reach 0 before it reaches D for sure. So U0 is equal to 1. On the other hand, UD is equal to 0 because if the process starts with D, then the process will never reach 0 before it reaches D. So the probability is equal to 0. Now, Ui can be decomposed into 3 possibilities. Either the process stays in the same place, so that probability is Ri times Ui, or the process goes right, so the probability is Pi times Ui plus 1 because the process goes right, or the process will go left. So the probability is Qi times Ui minus 1. So we can move Ri, Ui to the left-hand side. So Ui minus Ri times Ui, that is equal to Pi plus Qi times Ui. Recall that Pi plus Qi plus Ri is equal to 1. And also we have the right-hand side like this. And if we organize this equation, we will have this equation. And then we know that what is Ui plus 1 minus Ui? Ui minus 1, Ui plus 1 minus Ui is equal to Qi over Pi times Ui minus Ui minus 1. So that is like this. And if we let Vi be Q1, Q2 up to Qi over P1, P2 up to Pi. And also we let P0 be 1. And then we know Ui plus 1 minus Ui can be written as Vi over V0 and U1 minus U0. And now we put in I being equal to 0. So we know that U0 minus U1 is like this. And in the same manner, we know U1 minus U2 is like this. And we keep going up to UD minus 1 minus UD is equal to this. So if we sum over all these equations, and we know that U0, U1, U2, all of these can be cancelled out, and we are left with U0 minus UD. And we know this is equal to 1 and this is equal to 0. So 1 minus 0, we are left with 1. And the right hand side, we are left with this. So we solve for U0 minus U1, which is V0 over summation Vi. Now, if we know U0 minus U1, then we put it back here. In general, we know Ui plus 1 minus Ui is. But Ui plus 1 minus Ui is. So, and if we change order, we know Ui minus Ui plus 1 is equal to this. And V0 can be cancelled out, so we are left with this. So, Ui minus Ui plus 1 is equal to this. Ui plus 1 minus Ui plus 2. We can just plug in I plus 1 here. So we have this. And we keep going. So in general, we can solve for Ui. And if we can solve for Ui, how about U1? Because that is the value we are really interested in, right? So we just plug in 1 here. So we let I equal to 1. So V1 plus V2 up to Vd minus 1 over V0 plus V1 plus up to Vd minus 1. And that is 1 minus 1 over summation Vj. So we have solved for U1. And we know what U1 means. U1 means P1, the conditional probability that the process starts from 1 and it will reach 0 before it reaches D. Remember, T0 means the first heating time of state 0, and TD means the first heating time of state D. So T0 less than TD, that means the process hits 0 before it hits D. And furthermore, we can look at this quantity, rho 0, 0. This quantity means the process starts from state 0 and it will at least visit 0 again. So that is rho 0, 0. And this quantity is equal to R0. That means the process stay, the probability that the process stay in 0, plus P0 if the process has gone right. So P0 times P, so because the process has gone right, so it is now at 1. So P0 times P1, then T0 less than infinity. Because even if it has gone right, but we still want it to return to 0, so T0 less than infinity. So we know that if rho 0, 0 is equal to 1, that means this must be equal to 1. Because remember, if it is if this is state 0, then R0 plus P0 is equal to 1. So if we want the left hand side to be 1, P1 T0 less than infinity must be 1. And that is U1. So we know that summation Vj must be infinity, because remember what is U1? U1 is like this. So if we want this quantity to be 1, the denominator here must be infinity. If we want this denominator to be infinity, that means Vj must be big, right? So summation Vj must be big. So, but what is Vj? Vj is here. So if we want Vj to be big, that means Q must be big. So generally speaking, we know that if we want P1 T0 less than infinity, which is U1, to be 1, then Qi must be big. So if you can think about a simple random walk where Pi is equal to P, Qi is equal to Q, meaning all the probability are the same. And then in this case, Rj, oh, I'm sorry, this should be Vj, will be equal to Q to the power of j over p to the power of j. Then summation of this will be less than infinity if q less than p. And this quantity will be infinity if q is greater than or equal to p. Limiting probabilities or co-stationary distribution. Recall that Pn represents the n-step transition probability matrix, and that is equal to p to the power of n. P represents the one-step transition probability matrix. And when n goes to infinity, we can show that all rows of p to the power of n will converge to the vector pi, which consists of pi 1, pi 2, up to pi j. And the interpretation of pi j will be the long-run proportion of time that the process will be in state j. So for example, this is P4, and this is P8, and we can see that eventually this row, each row of this Pn will converge to pi. This will converge, all of them will converge to pi. And here we have a homework. I'm going to ask the TA to post the homework online. And basically, you are given a transition probability matrix, and you are going to check if you let n goes to, for example, 1000, and then each row of this transition probability matrix will converge to the same pi. And what does that mean in practice? Periodicity definition. Period of I, some state I, which is an integer, is defined as the GCD of n greater than 0, PIIN greater than 0. What does PIIN greater than 0? That means the process starts from I, and after n step, there is positive probability that this process will go back to I. And GCD is greatest common division. We give an example here. So state I will go back to state I after 3 steps, or 6 steps, or 9 steps. So obviously P11n is equal to 0 if n is not equal to 3, 6, 9, 12. And P11n is greater than 0 if n is equal to 3, 6, 9, 12. So 3, 6, 9, 12, the GCD is 3. So D1, that means the periodicity or period of 1 is equal to 3. And similarly, D2 and D3, all their period or periodicity are equal to 3. Theorem. Periodicity is a class property, which means if state I has period D and state I and J communicate, state J also has period D, so Di will be equal to Dj. Now we prove that. First, because I and J communicate with each other, so I can go to J. So that means there exists N1 such that Pij N1 is greater than 0. And J can go to I because I and J can communicate with each other. So Pji N2 is greater than 0. So what does that mean? That means I go back to I after N1 plus N2 steps. Right? Because I go to J after N1 step, and J go back to I after N2 steps. So I can go to I after N1 plus N2 step. And similarly, J can go back to J after N1 plus N2 steps. So Di, that means the period of I, is actually N1 plus N2 is divisible by Di, which is the GCD. And N1 plus N2 is divisible by Dj. So now, if we let J mean the state that this state collects all M, that pjjm is greater than 0, then we know that I go back to I after n1 plus n2 plus m steps. Why is that? Because I can go to j after n1 step, right? And j can stay in the same place after m steps, so n1 plus m. And then n2 step is j can go back to I after n2 steps. So I can go back to I after n1 plus m plus n2 steps. So that means the n1 plus n2 plus m is divisible by ni. So m is divisible by di. So di is less than or equal to dj. And similarly, we can prove that dj is less than or equal to di. So we can prove that di is equal to dj. A periodic. So the definition of a periodic means a state with period 1 is called a periodic. So for example, if we look at state 1, GCD of all possible steps that you can go back to 1 is 3 steps after 3 steps or 4 steps. But 3 and 4, their GCD is 1. So state 1 is called a periodic, meaning state 1 has period 1. Definition, partially recurrent. Partially recurrent means for some state I, the expected time that I can go back to itself I is less than infinity. And null recurrent means this expected time is equal to infinity, meaning it takes infinite time to return to itself. Remark, partial recurrence is also a class property. All recurrent states is a finite state Markov chain are partially recurrent. This should be all recurrent state of a finite state Markov chain are partially recurrent. Ergodic, partially recurrent periodic states are called ergodic. Theorem, for an irreducible ergodic Markov chain, limit n goes to infinity Pij n exists and is independent of I. Furthermore, we can let pi j be limit Pij n, and then pi j is the unique non-negative solution of these two equations. And recall that ergodic Markov chain means all states in this Markov chain are partially recurrent and a periodic. And why is that? If we look at probability xn plus 1 is equal to j, and we can condition on xn is equal to I times probability xn is equal to I, and we sum over all possible I. And this is Pij, right? So we have summation Pij, probability of xn is equal to I. Now, if we let n goes to infinity, and we know that this will go to pi j, and this will go to pi I. So we have this pi j is equal to summation Pij pi I. And for every component of the stationary distribution vector, we can write like pi is equal to pi p. Now we give an example here. Suppose this is the one-step transition probability matrix, and now we want to find the stationary distribution pi. So we can write like pi is equal to pi p. So this is pi p. So pi 1 is equal to, so this is based on the matrix multiplication. So this is pi 1 times, so this is this times this row times this column, right? So pi 1 times 0.5 plus pi 2 times 0.3 times plus pi 3 times 0.2. And similarly, you have the second equation, the third equation. And also remember pi 1 plus pi 2 plus pi 3 must be 1. Then you can solve pi 1, pi 2, pi 3.